Okay, in sections 8.5 and 8.6, we're going to talk about complex numbers, but we're going to do it the trig way. So let's do a quick review of what you've seen of complex numbers when you took algebra. Complex number is any number written in the form a plus bi. A is the real part, b is the imaginary part, and I is basically equal to the square root of -1. And you talked about the fact that complex numbers are all numbers. Every single number you know, real numbers and non-real numbers or imaginary numbers are all complex numbers and can be written in the form a plus bi. Okay, you've done things with complex numbers like added them. You've multiplied them. You've divided them. You've raised them to powers. Okay, so basically we can do most of that same thing with complex numbers in what we call trig form, but there's a couple things you couldn't do in algebra that we can now do by writing complex numbers in trig form. So that's what we're going to talk about in 8.6, so something new and exciting to look forward to. But first, before we can do that, we have to be able to convert a complex number in rectangular form or standard form to a complex number in trig form. So we have to understand the idea of graphing them in what's called our complex plane. Different from our Cartesian plane, which is the old XY coordinate system with the horizontal axis is the x-axis, vertical axis is the y-axis. This is where we only graph real numbers, okay? Now with our complex plane, we can graph real and non-real numbers, okay? So my horizontal axis is basically the real part of the complex number, the real component, and my vertical axis, my imaginary axis, is the imaginary part. So basically, if I have the complex number 2 plus 3i, so I know that a is 2 and b is 3, so I'm going to go to the right 2 and up 3. So here's the point that represents the complex number 2 plus 3i in the coordinate system. We can think of that as an ordered pair, so to speak, in our coordinate system. So if I have -4 plus I, that's 1i. So I go -4 on the real axis and up 1 in the imaginary direction. And here's the point that represents the complex number -4 plus I. Okay, 6 is a real number. It has no imaginary part, so we can think of that as 0i. So a real number is going to be located on the real axis. So I'm going to go to the right 6, but I'm going either up or down in the imaginary direction. So this is the real number 6 on the real axis. Part D, -2i is a pure imaginary number. Its real part is 0. Its imaginary part is, -2. Okay, so if I have a pure imaginary number, then it's located on the imaginary axis. So I don't go left or right in the real direction, I go down 2. So this point here represents the complex number -2i. And then we have here, we have square root of 3 minus I. So that square root of 3 is my real part. Now, we have to get an approximation, which is about 1.7 for graphing. And then my imaginary part is -1. So I'm going to approximate about 1.7, and I'm going to go down 1. Whoops, a little tight here. So this is the point, square root of 3 minus I. Okay, so you have to be able to graph them in order to write them in trig form. Or typically, it's more helpful. Okay, here we go. The trig way. How do we do complex numbers the trig way? Well, I just want to mention this, that our book will talk about a complex number is represented by a vector or a position vector, which basically has its initial point at the origin and terminal point is somewhere in the system. So ultimately, if we're talking about this point here that represents my complex number a plus bi, we could say that that is the end point of my vector, position vector. We aren't studying vectors, so we won't talk about the relationship between them, but you will see them in diagrams in the book, My Math Lab. All right, so how do we write it in trig form, a complex number? Well, we talk about R being the absolute value of that complex number, or oftentimes called the modulus. Okay, so if I look at my diagram, if I talk about this complex number a plus bi, it's the point A, B in the complex system. So I can see then that my horizontal distance is A, my vertical distance is B. So R is basically the length of that hypotenuse, or if we talk about distance, we could use the distance formula. So if we say R is the distance that point is from the origin, because that's what absolute value is, a distance. Okay, and we're familiar with that, square root of a squared plus b squared. We found R previously, same idea, except we're using a and b instead of x and y. Theta is called the argument of the complex number, and we're talking about the smallest positive angle in standard position that passes through that point. So this is very similar to what we saw when we talked about angles, trig functions of angles with the point on the terminal side. Okay, we know then that the tangent of this angle theta is equal to b over a, or what we used to say y over x. So if I wanted that angle, I can use the tangent function. Okay, so here we go. If I want to take a complex number in rectangular form, basically I have a plus bi. So I want to rewrite a in terms of r and theta, and b in terms of r and theta. So if we go back over here and use what we already know, our SOHCAHTOA, cosine is a over r, adjacent over hypotenuse, if you want to think of it that way. Or I guess we also talked about x over r if we were talking about a reference triangle in another quadrant. All right, so now we're just using a for x. So if I solve that for a, I get a is equal to r cosine theta. So I can substitute here. Same thing with sine. B is equal to r sine theta, so I can substitute there. Okay, now the thing is, we notice that this is a little redundant to find. We would be multiplying by r in two places. So we like to say, oh, we don't want to do that twice. So we factor out the r. And then we don't want to have to use these parentheses around sine. So we write it as r times the cosine of theta plus I times the sine of theta. So ultimately, we put the I in front of the number because the sine of theta is a value. Okay, so here's the trig form that you're going to want to know. And we can write it in what's called compact form, which means you don't have to write the cosine and the sine and write the angle twice. Okay, so the compact form is basically r CIS theta. CIS stands for cosine I sine theta. Okay, so we're going to convert complex numbers in rectangular form, a plus bi, to trig form, r cosine theta plus I sine theta. Okay, so very helpful if you graph first. I have a lot of people that'll skip this step, and it makes life more difficult in certain situations. So get an idea of what quadrant or what axis your complex number lies in the complex plane. Notice how I have the real and imaginary axes. So if I have the complex number 4i, then we know that is 0 plus 4i. So it's pure imaginary, which means it's on the imaginary axis 4 units up. Okay, so here's my complex number 4i. All right, what I want to know is what's the absolute value of that complex number? And we said that r is basically the distance that that complex number is from the origin. So the absolute value is the distance. Now, if you need to, you can use this little formula, right? The square root of a squared plus b squared. But I don't need to do that because I can calculate the distance because it is vertical, and we can always do that without having to use that formula. So to me, basically the distance is 4. Okay, so r is 4. Now, what I want now is kind of what we think about as if that's the terminal side of my angle in standard position. Here's my angle theta. Okay, so theta then is 90 degrees. So I didn't need to use any fancy stuff. I could easily get it from the graph. So if your complex number lies on an axis, the graph saves you time and energy. All right, so we're saying that my complex number 4i can be rewritten in trig form as r times the cosine of theta. My theta is 90 degrees plus I times the sine of theta. So that's the long way, which I'm going to do a little bit in the beginning until you get comfortable with it. Okay, so these two are equivalent. So this is the trig form. All right, don't find the cosine and the sine of 90 or you're going to go back to rectangular form. Okay, let's do another example. Whoops. It's down here. Okay. So z is -3. That is a real number. There is no imaginary part. So it's located on the real axis at -3. Okay, so what do we need? We need r and we need theta. All right, so r is the distance from the origin to that number. Well, I can see the distance is 3. Remember, distance is always positive, or we say it's the absolute value of that number. So r is always positive. Theta is, if that was the terminal side of my angle going through that point, theta would be the least positive angle with that terminal side. So I can see theta is 180 degrees. Okay, so if I want to write -3 in trig form, I take r times the cosine of theta plus I times the sine of theta. You're always going to have that same angle in those two arguments of cosine and sine. Now, if we want to see it in the compact way, then compact form, it would be 3 CIS 180 degrees. So just depends on which way you want to write it or asked to write it. Okay, now gets a little crazier when they don't lie on the axes. So here I've got -5 minus 5i. So A is -5 and B is also -5. So I'm going left 5 and down 5. So here is my complex number that I'm looking at. Okay, I want R. R is this distance. Okay, so R, remember, is the square root of A squared plus B squared. Here's where I would use my formula, which came from Pythagorean theorem or distance formula. All right, so r would be the square root of negative 5 squared plus negative 5 squared. So that's 25 plus 25, which is 50. We should always simplify our radicals. That's 25 times 2, so that's 5 square roots of 2. Notice there are technically two values here. Oh, whoops, I'm sorry. No, we already did that. That wasn't very smart. Let's go back because we assumed we're already taking the positive root since it's a distance. Okay, now to get theta, maybe you already know what theta is, but let's think about it. This would be my angle theta. Okay, if I looked at my reference triangle like we've done, I would see that this distance is negative 5 and this distance is negative 5. So ultimately, I have a isosceles right triangle, which means this angle here is 45 degrees if the two legs are the same. So that means my angle theta is in quadrant 3. It has a reference angle, so theta prime is 45 degrees. So what's the angle that terminates in quadrant 3, whose reference angle is 45 degrees? Well, it's going to be 225. Okay. Now, so here's what I always say. If A and B are the same value, as in if I talk about the absolute value, ignoring the sign, they're both 5. It doesn't matter if it's positive or negative, but the same distance if we ignore the direction. Okay, then you do not, you should know that it's an angle with a reference angle of 45 degrees. Okay, if not, you can use the tangent and the A over B, which we can do in another example. All right, so if I want to write negative 5 minus 5i in trig form, it would be equal to r, which is 5 square roots of 2, times the cosine of 225 plus I times the sine of 225. Okay, so here it is in my trig form. Now, if you're asking yourself, why has she only done degrees? Which is painful for me because I really prefer radians. We could write it in radians as well. It could be 5 pi over 4, and those could be replaced. The unfortunate circumstance is that in our book, they rarely use radians in this section. So that's why I typically stick with degrees. Okay, one more example. All right, we have the complex number negative 10 plus 10 square roots of 3i. This is a little tricky right here, and books will write it differently. Okay, so let me rewrite this. Negative 10 plus, what that is saying is 10 square roots of 3 times I. Now, it's hard to tell. And the way it's typed here with my equation editor looks like the I is under the square root. So a lot of times what you'll see instead of this way is you'll see it written as 10I square roots of 3. So they like to put the I out front so you won't think the I is under the square root. And you're probably saying, well, I's can't ever be under square roots, but they can. That's the cool thing about doing complex numbers in trig. Okay, that's another video. Okay, so that means then that I have A is negative 10 and B is 10 square roots of 3. Now, so it doesn't really matter that I have the actual value of 10 square roots of 3. It's positive. So what I really want to know is what quadrant is this complex number located in? If A is negative, I go to the left, and B is positive, I go up. Okay, so here's my complex number located in quadrant 2. That's what I need to know, the quadrant. Okay, this, I want to know the distance here, which is r. So r is the square root of a squared, negative 10, and b squared, 10 squared, so 3 squared. So I end up with 100 plus 100 times 3 is 300. Square root of 400, which is 20. So r is 20. I now need my angle theta. Okay, so basically, if I'm trying to find theta, I'm using this is where I can use the tangent. So I know that the tangent of theta is equal to b over a. If you want to label it, you can. We know a here is negative 10, and b here is 10 squared, so 3. Or think of it as y over x. Okay, so I know that it's going to be that ratio, b over a. So to find the angle, then, you're going to use the inverse tangent. And we know that's going to be a problem because inverse tangent is only going to give you an angle in the interval from negative pi over 2 to positive pi over 2, or negative 90 degrees to 90 degrees. Okay, we know that. So ultimately, what we're going to have to do is find the reference angle using this formula, so to speak. Okay, so my angle theta is going to be the inverse tangent of, oh, wait a second, sorry. I want to do this so you can see it first. Let's do this. Okay, so the tangent of theta, then, in our situation is 10 squared to 3 over negative 10, which simplifies to negative square root of 3. Okay, so really I don't need to use my calculator because this is an exact value. I know there's an angle if I talk about the reference angle, basically in quadrant 1, I know there's an angle whose tangent is square root of 3, and that is 60 degrees. So that's what I'm saying here is the reference angle is 60 degrees. So my angle theta in quadrant 2 would be 180 minus 60 would be 120 degrees. Okay, if you didn't happen to know this exact value, unit circle, or if that wasn't an exact value that was unit circled, then you could use your calculator. Okay, so trig form of my complex number is negative 10 plus 10 squared to 3. I'm going to leave it like this since I already started it, is 20. And if we wanted to just go to compact form, CIS 120. So there it is in trig form and rectangular form. Okay, so once we can convert now, we can, oh, whoops, we've got to convert the other direction. Then we can do operations with these numbers. Okay, so to me, converting from trig form to rectangular form is quicker, easier, because all you're doing is evaluating cosine and sine of an angle. Okay, so here I've got 12 cosine 240 plus I sine 240. So I'm going to take 12, and it doesn't matter if you want to distribute the 12 first or find the values and then distribute. I typically find the values and then distribute. So ultimately what I need here is the cosine of 240. And if it's a unit circle value, you give an exact value. If it is not, you'll have to use a calculator. So cosine of 240 is negative 1/2 plus the sine of 240 is negative square root of 3 over 2, and then don't forget the I. All right, and then we can distribute the 12. So ultimately, if I had my complex number 1 unit from the origin, it would have these two coordinates, but it's 12 times out, basically. All right, so what have I got? I've got, if I multiply by 12, I get negative 6 and minus 6 squared to 3i. So this is my rectangular form, or a plus bi form. All right, now notice the second example here. My angle is not a positive angle. That happens. The only reason they say give that positive angle is because they want you to give a specific angle so they can check it. And it's just a little more proper and it's easier to evaluate. So it's up to you how you'll see them other ways. So let's think about that. If you're good at evaluating this with the negative angle, fine. Cosine of negative 30 is going to be square root of 3 over 2. Okay. If you don't like that, then what can you do? Find the least positive angle coterminal. So add 360 and you get 330 degrees. Maybe you're better at that. The sine of 330 degrees is negative 1/2. And then you can distribute the 5. So it's 5 squared root of 3 over 2, there's my A, minus 5 over 2, there's my B, I. So here is my trig form of that complex number. All right, now how about compact form? And doesn't matter to me, I don't want you to write this out because that's the point of using compact form. You don't want to have to write it out. So ultimately, then, you can if you want to, though. It doesn't matter to me. So I've got to take square root of 3 times, what do I need? I need the cosine of 270. The cosine of 270 is 0. Okay, and then I need the sine of 270. Sine of 270 is negative 1. And don't forget the I. And then you can distribute. Or if you prefer to distribute first, doesn't matter. In this case, with the compact form, I wouldn't distribute first. So square root of 3 times 0 is 0. Square root of 3 times negative 1 is negative square root of 3. And instead of putting the I out back, if you do, you have to really space it out. But typically, you'll see it like this, I square root of 3. So notice there is no real part, pure imaginary. So that number, if you're thinking about graphing it, think about it's on an angle of 270 degrees. So where is it going to lie? It's going to lie on the imaginary axis because it's a pure imaginary number. So you can kind of relate those. All right, for CIS 118, well, here's where I would distribute first because 118, I don't know the exact value, so I'm going to have to use my calculator. And if you're going to put it in your calculator, you might as well put it all in once. So I would write it as 4 cosine 118 plus I times the sine of 118. And then you can just punch those, oopsie, I forgot to multiply the 4. Let me squeeze it in here. So maybe I'll write it this way. So how about if I say plus 4 times the sine of 118, and then I'm going to take that times I, because that's my coefficient on I. So if you put this in your calculator, round to whatever number of decimal places, I'll go to 3. Negative 1.878 would be my A, or my real part. My B, or my imaginary part, will be 3.532. So basically then, here's my complex number. And if we think about it, just do a quick check and see if that seems reasonable. An angle of 118 degrees terminates in quadrant 2, right? So my complex number is 4 units away from the origin in quadrant 2 on the terminal side of an angle of 118 degrees. So its A value should be negative and its B value should be positive. And there you have it, converting. In the next video, we'll look at multiplying and dividing and raising complex numbers to powers.